Thank you very much for coming in this morning, and we're very happy to have you all here. It's my pleasure to introduce our first speaker, Tim Denison. Professor Denison holds a Royal Academy of Engineering Chair in Engineering Science and Clinical Neurosciences at Oxford, where he explores the fundamentals of physiologic closed-loop systems in collaboration with the MRC Brain Network Dynamics Unit. Set up.
Thank you very much. Bonjour, and my apologies for speaking in English. I'm going to talk about the design of pediatric devices, systems for children, but I'm representing a much larger team called the Cadet Group, which is the Children's Adaptive DBS Epilepsy Trial team, and it's combined at Oxford, but led at University College London, Great Ormond Street. I do have a few disclosures I'd like to start with, the most pertinent being that I'm a founder of a device company, Amber Therapeutics, that builds a research system that's used in the cadet trial itself. I think it's important this morning to start thinking about the impact of brain diseases on society. And so this is a synopsis that was done in Neuron in 2014, and what's shown in the top row is the impact of different disorders, from anxiety on the right to brain tumors on the left, and the number of millions of people in the EU, so this is focused on the EU alone, that are impacted at any given time. So you can see upwards of 61 million people with anxiety at any given instant in the EU. The middle row in green is the cost to treat them in euros in a given year, and then the bottom in orange is the aggregate cost to society. You can see that each one of these burdens is running on the order of 10 billion euros per annum, oftentimes approaching over 100 billion in the cases of, say, dementia or addiction. And so our opportunity, to actually say for this entire day, is to give thought about what we can do with technology to try to improve the situation for these people suffering from these conditions. The first thing that often comes to mind is, why not pharma? So this is a plot that was constructed in 2012. The Economist, actually 2 weeks ago, just updated this, but the trend is largely the same. And what it's showing is, on the y-axis, the number of drugs that are released for $1 billion of US investment, and this is inflation adjusted, over time. Notice it's a logarithmic axis, so it's a very sharp drop over time, which is going by linearly. And so right around the turn of the millennium, it costs about $1 billion of investment to release a drug. So this is a pretty significant downtrend and a real headwind in the area of treating brain disorders. And you can see the pharma people make fun of themselves a little bit. They came up with this word of E-Room's law. And what E-Room is more spelled backwards. And so this is to contrast to the evolution of electronics over the last several decades, which followed Moore's law's progression, which of course is not a physical law. It was more of an empirical observation made by Gordon Moore, the founder of Intel. This shows a microchip and its size basically starting the year I was born, and how the chips would evolve with me over time. And so what happened, you can see, is the drop. It's not that there was a drop in innovation in 2014, it was that actually you could no longer fit the chip onto a pixel. And so they stopped plotting it on the graph. You basically just can't see it anymore. And so one of the opportunities for us is to think about what we can do to apply the innovations in microelectronics and bring those to bear in the space of treating brain disorders. So the vision that we're exploring in this talk, and I've added in the last bit specifically for pediatrics, is to think about designing devices that really mimic and restore physiology. And by mimicking, I mean both predicting our changes in our needs, so symptom patterns, sleepiness and awake, just like you know tomorrow morning you're going to get up at a certain time and your body actually has a circadian rhythm. Devices themselves can anticipate this and look forward to what your needs might be. Similarly, There's a responsive element where we have sensors and classifiers, and we can actually then say, based on my moment-to-moment needs and how those change, what do I need to adjust the therapy? And then ultimately, by respecting these kinds of rhythms, in the near term, we're thinking about how we could, say, apply better symptom management with devices. But maybe in the future, we could restore rhythms and slow degeneration. Now, this is definitely a vision and an objective, but it's certainly a worthy one to have. Could we say slow dementia or Parkinson's disease if we could use devices appropriately to break the cycle of degeneration? And that gets to my last point, which is really the emphasis for pediatrics, is there a way to restore lives with earlier interventions, as opposed to waiting very long down the treatment pathway? Can we actually put devices in sooner and have a larger impact on lives? So the first part of the talk is I'm going to give a basis for where we are in brain stimulation today. And then second half, I will branch over and discuss the challenges of applying those into pediatrics. So first, let's see, where are we? So this is a video of a gentleman with a central tremor. And so on the left, he actually has a brain implant. On the left, his device is turned off, and on the right, his device is turned on. And you can see that there is a marked impact with the brain stimulation applied. However, there is some residual tremor. And when we look at the graphs, we see when it's blinded, we, in the case of Parkinson's, say there's about a 30% improvement in patient symptoms. So even though we're seeing the benefit, there's still work to be done. And one of our challenges is how to improve the therapy and get the tremor reduction as he's going about his movement, but not turning up the therapy so high that he starts to get side effects, such as impacts in his speech or the feeling of tingliness, paresthesia in his body. So what he has inside of him is actually what we might think of as a brain pacemaker. So in his chest, there's a device that has a battery, an energy source, electronics for creating a pattern, electrodes that are then tunneled up through his neck, and then a neurosurgeon will place the electrodes deep into a specific area. In this case, it's a thalamus for the treatment of tremor, and this is a different area of the thalamus. For this particular patient, they're looking at epilepsy. Historically, this first generation devices was created to replace a lesion. So what would happen is a surgeon would go in with an electrode and basically burn away that area of the tissue and destroy it to provide therapy. And the idea of the electronics was to replace that damage with instead a fixed pattern of stimulation. But it was definitely fixed. It was not changing and responding in any way to the patient's needs, except perhaps with a little patient programmer that they would adjust up and down, similar to a television remote controller. But right around 2000 to 2010, the early millennium, we started to think about branching away from this idea of a fixed pattern of stimulation that's on all the time in the same way. Instead, thinking about dynamics, and Ed Boyden, the co-founder of optogenetics, coined the phrase a brain coprocessor. And the idea is, instead of just applying stimulation, fixed patterns of stimulation, we'd also look for signals of interest coming from the body, processing those signals, classifying them and extracting features, and then use that to adjust in real time how we were applying the stimulation. So that could be changes based on whether you're asleep or awake, changes based on whether you're having a seizure or not in real time, but thinking about the dynamics of physiology and how those can be applied. So because of the broad audience, make sure I don't lose anyone, an analog for you to think about intuitively is like a furnace or a boiler. This is the first generation of technology. No matter what the weather was or the temperature, you put out a fixed amount of BTUs, fixed amount of energy, and the device was not responding. So what we want to do is identify the equivalent of the thermostat that measures temperature and then makes adjustments to then control this device in real time. So because this is what we really care about, similar to the temperature in your room, we don't want to know what the British thermal units are coming out of the furnace. We care about what the temperature is. Similarly, the clinician or the patient wants to identify their symptoms and the optimal treatment, and then have the device do what it needs to do in order to maintain that steady state. So one of the big areas of opportunity right now for us is identifying what is that sensor, what is that equivalent signal of temperature when we think about brain disorders. Well, the first thing is to think about areas that we can extract information from the brain. So of course, we can put sensors on the head, such as EEG, and the advantage is that that's non-invasive. However, we're already putting leads into deeper brain areas, such as the thalamus or the basal ganglia. So we already have leads that are penetrating into the brain, and we can look for signals off of those. And those range from laying electrodes on the surface of the brain for electrocorticography, or with penetrating electrodes, looking at local field potentials, kind of the average ensemble activity from the brain, or individual spikes from neurons. And so the signals, the challenge that we have from a technology standpoint is these are about 1,000 times smaller than a cardiac pacemaker. So this is why we're still struggling to get this technology out, is it's about 3 orders of magnitude smaller than a cardiac system. And so a lot of innovation has to go into getting these signals reliably. And in fact, spikes, you might have heard in the news with Neuralink, they're trying to get down at this resolution, and they've had some issues with their implant pulling out of the brain. So I'm going to speak for the remainder of this talk mostly about field potentials and ECOG, kind of this ensemble activity. So it's like me reading the room, where instead of hearing one of your individual voices, I just listen to the amount of applause and kind of gauge your activity and broadly. And that's a much more reliable technique. So even at that scale, there are different ways to kind of probe the nervous system to get a sense of what state it is in. And so one is the evoked potential, so I can evoke a response. So that's like give an auditory stimuli, flash a light, look at how your brain responds to electrical stimulation. That's one kind of an active probe. Think about like radar, kind of you ping and listen for a response. The other is to just passively listen. And so there are all these rhythms in your brain. You all have these rhythms. So as you're going through and processing information, your networks will have discrete frequency bands where you can see activity wax and wane. So this is time going by, looking at kind of the radar ping coming back. Alternatively, this is more like an AM radio, like a radio dial, where we tune to a specific frequency, and we can look at the activity in the brain and use that as the energy in a specific band, say at 10 hertz, comes and goes. And so the area that we focus on currently within our laboratory is on the LFP and ECOG, as we said, but also looking at these rhythms. And once again, to give you an analogy, you can think of these as musical notes kind of aligned along this axis. And as time goes by, we look at how these different frequencies come and go, and we look for a pattern match. So similar to you see the beginning of Beethoven's Fifth, we look for a signature like this and say, this is the onset of an epileptic seizure. It's time to actually take effect. So in a way, kind of identifying that analog of a musical note in the brain's frequency and applying that. So to give you a sense of how this can be applied, this is coming back to the example of a gentleman. This is a different research subject with an intention tremor. So as they go about their activities of daily living, as they intend to move, the more they're focused on movement, the more that they actually have a tremor. So Aisha Gundez was the PI, and she's a research tool that my team developed to put an electrode on the surface of the brain over the cortex to do ECOG, measure someone's intention to move by looking at their brain rhythms. So there's an analog of that musical note at a specific frequency. When the person is idle, you can hear that tone, if you will. It has a strong rhythm. When they start to initiate their movement, that then triggers the device to turn on and apply stimulation in the thalamus. And so if done well, the cortical electrode will actually say the patient is thinking about movement. It's now time to turn on the device. That stops their tremor from being elicited. But then when they no longer need their therapy, that's also detected by the return of the musical note, that brain rhythm, and the device turns off. And thereby, perhaps we can improve the therapy for the patient, providing maximal tremor relief while trying to keep the side effects to a minimum. So here is the movie of it actually in operation. So we'll start by showing just the baseline for the patient. So it's going through an activity of daily living of pouring a glass of water. On his arms are little sensors, accelerometers, and gyroscopes just to help to objectify the motion. So you can see the tremor is rather severe, spilling water onto the table. So now they're going to activate this brain-computer interface. So the top band is the raw signal coming from the surface of the brain. It's very actually hard to see. It's kind of like looking at musical information. But what we can do is tune into those specific notes that represent the brain rhythm and then use that, as we said, to gate the stimulation. So as he rests, that tone comes back. You can see high energy. When he initiates motion, those notes go away, and we can ramp the stimulation up and thereby avoid tremor. And now his hand goes down, note comes back, and we know we can turn the signal off. And so the red bar here is synchronized with the movie. And so you can see with Aisha Gundaz's prototype, she was able to demonstrate over time that she could have a reliable closed-loop system, well, I should say adaptive system, to treat the tremor. And practically what's good is in terms of providing the therapy while trying to minimize side effects, but also the amount of energy required to provide the therapy was dropped by about a factor of 2. And that means the longevity of the device is almost doubled. And so you can think about going in for battery replacement, if you have a primary cell device, requires surgery. And so by actually pushing out that surgical time by a factor of 2 has meaningful benefits for the patient and also saves the healthcare system money. And so there's some very practical advantages of this technology as well. So this gives you a sense of really where we're at in the area of tremor and Parkinson's disease, these just starting to do closed-loop systems and looking at adaptive ways to optimize therapy. And as of today, 2024, this is still, in the case of neurotechnology, the dominant application in my space of research for treating brain disorders. However, there's an emerging interest in the area of epilepsy, and that's where I'm going to focus on specifically in my own research working on pediatric applications. So I'm going to start, and a key message for my group is that this is multidisciplinary research. So the chief investigator and the lead neurosurgeon is Martin Tisdale at the Great Ormond Street Hospital for Children. It's affiliated with University College London. And there's neurosurgeons, neurologists, neurophysiologists. Similarly, there's another children's hospital in London who we collaborate with, the Evelina, that's part of King's College, and then the engineering team that I help supervise. And so it's all of us working together across the disciplines in order to make this come together and be successful. And that also includes statistics. And R&D represents the regulatory and the ethics side of this research as well, which is also, of course, incredibly important, and we discuss in the second half of the day. So why focus on children and drug-resistant epilepsy? First, just the numbers. About 600,000 people have epilepsy in the UK, more than 45 million in the world. Some people do respond well, majority to medication, but still about 1/3 are unresponsive. And so what can we do to help these people? Those frequent uncontrolled seizures result in injuries, poor quality of life, deficits, and risk to life from SUDEP. One thing I sometimes do with my students is I'll give out a number to every one of you in the audience. And what I say is I'm going to put a random number generator on at one of my slides. And I'm going to see what number it is, and you have to lay on the floor and roll around for 30 seconds, and we're going to watch you. And just the threat of that to the students is enough to give you just a sense of the anxiety that epilepsy patients face. They don't know when. One of the biggest burdens is the uncertainty of when the seizure might come. And facing that day to day has a severe impact on their quality of life. There are costs to the NHS. I support a social health care system, so we work a lot with economics and designing technology that's appropriate. And we also, an advantage is we have a clear biomarker and some objective outcome measures to know the success of our intervention. But really what I want to emphasize is the early treatment of epilepsy could perhaps break a vicious cycle, where oftentimes when children have seizures, that then creates a long-term cognitive deficit and impacts their family life. It also can increase their probability of further seizures. And so there's this vicious feedback loop that can keep going. And the idea here is, can we get in with the device earlier and have an impact on that child's life, help them to stay in the school system, and help to basically ease their family's load, and so the overall family can also improve its quality of life. There is a rationale for DBS for epilepsy. The first is physiological, is if we go and put the leads into specific brain targets, oftentimes in the thalamus, this is the anterior nucleus of the thalamus, and the central median thalamus, we can engage these broad networks. So that electrode is on the order of 1 millimeter. So just 1 millimeter square of tissue, say, that we're activating. How can we possibly have an impact across the entire brain for generalized epilepsy? Well, if we can get into these specific targets, because of the large-scale projections that go across the brain, we can have a very large impact. Similar to, say, going into a strike. If I want to strike, I go to the central train station. I have a big impact across the entire network, as opposed to going out into some local area where I might have little impact. Same objective is there. People have tried in little pilot studies. In fact, we did Martin Tisdale pulled together 35 small pilot studies, children ranging from 4 to 18, different types of seizures. And on average, this is the percentage treated, number of patients with, and this is the percentage of seizure reduction. You can see a very large number. In fact, the majority are getting a significant seizure reduction, and specifically in this central medium thalamus, one of those key network hubs, like we say, the northern train station, where we can actually have a large impact on the brain. So there is evidence that we can go into pediatric epilepsy and make a difference. The challenge is sometimes practical in terms of the device that's used. So we're thinking about designing a deep brain stimulation device for a child. The way the field got started was really repurposing a device that was designed for a 70-year-old with Parkinson's disease. And there are challenges associated with that that we'll get into. And one key element is that oftentimes we'll think as adults that, oh, they're just little adults. So we'll just shrink. They're just little, they're tiny versions of us. And that's not at all the case. And we need to really think about some of their unique needs. And so that's really where I want to spend the next few minutes kind of deriving those challenges and some of the opportunities we're looking at. So first is we can go back to this history where there is experience with established technology, 129 children who had subclavicular IPGs, so these were designed for adults. Oftentimes, instead of the system being implanted here then in the chest, it's just too big. So they actually have to go down to the abdomen. And so that's the kind of study that was done here. And looking retrospectively, saw about a 10% device infection. So 1 out of 10 children will suffer from an infection. The extension that goes to the neck can really have issues in terms of breaking. And you also think this is why children are not small adults. They're going to grow. So what's going to happen is that you've got a wire that's been fixed. What's going to happen as the child grows? The hemorrhage, that's a concern about putting the electrode in where you actually hit a vessel. That's being worked on with just general techniques to try to improve it. Battery complications. So one of the issues is we talked about primary cell devices. We want a rechargeable system. So imagine your cell phone, you can only have 1 battery use and then it's done. And then you have to go buy a replacement. That's not really a viable technology for the children. So we tend to use rechargeable devices. but that recharge can cause quite a burden on them. Thinking about how do you maintain the charger, the battery runs flat. One of the challenges that I sometimes deal with is teenagers want to be in charge of their device, but they're also not very reliable at maintaining their device. And so I get called in to help to mentor them on what are the impacts for them letting their batteries go flat. But that's one of us for as engineer, how do we incentivize children to actually help to maintain their therapy? So some of those challenges, can we get closer to cochlear implants, which actually have a reported significantly improved approach to minimal risk? How do we make the device growth resistant? How do we improve the device longevity? So instead of going into a 70-year-old Parkinson's patient, this is say going into a 5-year-old. So their lifetime, the device has to actually last for much, much longer. How do we actually personalize and adapt the therapy? So as they grow over time, what might we need to adjust, especially as their brain develops and through their teenage years and through puberty? Remotely programmable makes it accessible to more people across the world. And then the last bit, which is really critical, is child and family acceptable. So you're going to hear from speakers representing lived experience. We talk with quite a few children. There's a young person's advisory group. So these are young children at the Great Ormond Street Hospital. And we can ask for their advice on how do we actually think about the technology, what are the elements of design we need to consider, what are their concerns that need to be mitigated in terms of what else, what might it alter? This is real concern. Will it change my personality? Will it change my memory? Will my parents be able to control me? Will people be able to read my thoughts? Some of the same concerns that adults have, children have very profound concerns as well. We need to make sure that they're comfortable with the technology. Especially in case of devices, how is it going to impact their ability to go about life? Can they maintain swimming? In case of a cranial mount device, can they still head a football? Things like this are practical and real considerations. So we've been dipping our toe, as we say, into this space very intentionally, thinking about a research platform where we modified, instead of the device being in the chest, there's some real advantages for putting the device up in the cranium, especially in terms of growth, so that we currently go down to children around 5 years old, because by then your cranium is relatively fixed, and we can put the device into a pocket. And then in terms of the adaptable nature of it, thinking about the algorithm toolbox for how do we actually tune the device for the child's needs, including circadian patterns, which in the case of epilepsy, there's a very strong dependence in many disorders where what happens to when your brain is in its awake state versus its sleep state also reflects a profound change in the probability or the nature of your seizures between daytime and nighttime. So this is a CT CAT scan of a device. This is not from one of the children. This is from one of our adults, but it gives you the sense this is from a Parkinson's-like multiple system atrophy. So the device basically sits in a little pocket in the skull, and then the electrodes are routed down, in this case, into the brainstem, but kind of similar area for the thalamus. So that gives you a sense of how the device sits in situ. We are actively pursuing the trial. There will be a story coming out on BBC from one of our first implants later this month that you can follow on. But the areas that we tailored in and really focused on is how do we make this acceptable for the child, especially that recharge experience. And the one thing we worked on was an adaptation for headphones, so they can watch movies or play on their tablet, and then the device is charging up. And we basically just make this part of their activities of daily living. And so what's nice with this is it's very reliable in terms of they know exactly where to put it. We can fit the headphones and tailor it for the child, and they can basically be entertained while the recharge is happening behind the scenes. And that also allows them to, being up in the cranium, gets rid of the issues with the neck and the subclavicular implant in terms of growth. We're still too soon in this journey to make any conclusions on infection risk. And I'd actually say in the whole area of cranial devices, including neuropaces devices, is still an area that requires further improvement. In terms of the adaptation elements, I won't go into this in much depth, but this is just to give you as the audience kind of a snapshot of the complexity and opportunity of these devices, where we have our cartoon of building a bioelectronic therapy with sensors and algorithms and optimization routines running inside the device. And that's what I really want to reinforce. That little device, just a few centimeters by a few centimeters, is really an implantable computer. It's full of sensors. We can program it with different firmware with the neurologists and really look to fine-tune the system. Meanwhile, the patients and their carers have control over the device. So and this is part of the feedback. They always have the ability to turn the device on and off as a requirement, and they can also turn on and off any adaptive modes. And so they always maintain control, and that's one of the elements of feedback that was provided to us. And then, of course, thinking about the data science, one of the areas that's really exploding at this time is because of our ability to gather sensors and classifying information, we can learn as a population. So historically, say we'll treat on the order of 10 to 20 children, or 10 to 20 subjects at Oxford. Now we can actually take advantage of these instrumented devices and look together as a community and perhaps take the ensemble data from thousands of patients, like they're doing at NeuroPace, and use that to further optimize the therapy. So just to summarize, I see this not as designing, but also redesigning devices for children. We've looked historically at some of the challenges, used those to create important design features for the future that are really relevant for the pediatric population. And growth resistance includes both the mechanical as well as our ability to learn. So probably what we learn about the brain, I'd certainly hope, in the next 20 years, we want the device to be able to benefit from as well. So similar to your cell phone that can be upgraded with new operating systems, the device really needs to have that capability as well to learn, and that'll be then growth resistant. So we're getting there, but there's still some challenges. I would like to say, and actually almost challenge the neurotech space, that instead of avoiding children, we actually see it as an opportunity, because if we can actually solve the challenges for a pediatric device, the challenges for an adult system are almost a subset of those, and so we can actually do even better for adults as well. I do like the idea of epilepsy as an area of focus, because I think it changes the way we're intervening with neurotech, where it's not, say, a palliative treatment hiding symptoms, but your Parkinson's continues. It's a new approach where we're actually going to go and intervene and change the lifetime long term, and perhaps even break the cycle of degeneration. And I think these discovery platforms do expand those opportunities. And so one thing I do want to represent as a field is I've given you two little snapshots, but there's active research, of course, going on in neurotech throughout all of these areas, and you'll hear more about this through the day. And I just want to wrap with saying this is a bigger vision, I think, for the community of taking advantage of electronics and not just coming up with, historically, these tonic stimulators, but really thinking about the capabilities of advanced technology to mimic and then ultimately restore physiology to care for patients. And that is really the ultimate goal, is to restore those lives. So with that, I'm happy to take questions. Thank you.